Hello friends, hope you are all well. I am going to talk briefly today about two distributions, normal and chi-square distributions. I have already uploaded this note. So normal distribution is something that you will know by now, and I am going to next talk about chi-square distribution and its relation with normal distribution. So these are two most important continuous distributions in probability and statistics. There is of course other distributions like t exponential, gamma, and these you have seen, and then there is also one f distribution. We will talk about them later. So chi-square distribution comes from normal distribution. So let's revisit normal distribution briefly. So I have a continuous random variable, that is probability x equal to y is 0 for all values of y. It is said to follow normal distribution if it has a probability density, and the formula is given as follows. This is something you have already seen. Mu and sigma turn out to be the mean, mu and sigma turn out to be the mean and standard deviations of these distributions. And if we define z is equal to x minus mu by sigma, then we have derived here that z follows normal distribution with 0 1. So if x follows n mu sigma, x minus mu by sigma follows n 0 1. The derivation is straightforward. So the idea is that we want to know the distribution of z. So find the distribution function of z, and the distribution function of z can be easily expressed in terms of the distribution function of x. And since the distribution function of x is known, so using that we can find out the density of fz, which turns out to be the standard normal density, that is normal distribution with mu equal to 0 and sigma equal to 1. So I hope you are able to follow this calculation. Next, I will quickly go to the chi-square distribution, which is the main target here. So the chi-square distribution is a continuous distribution, and let y be a non-negative valued random variable. So it is said to follow chi-square distribution with n degree of freedom. So it has one parameter n degree of freedom if the probability density is given by this formula. So if you compare this formula and with that of a gamma distribution, I hope you have gone through the previous note of some common continuous distributions. So this is really the PDF of a gamma distribution with parameter half and n by 2. So this chi-square distribution is really a gamma distribution with parameters n by 2 and half, and here this parameter n, we call its degree of freedom. So just like in the previous notes, we have computed moment generating functions for distributions that are not heavy tails. For example, exponential, normal, uniform, gamma. For them we have computed the moment generating function. So in the same way, since chi-square is also a gamma distribution, we can easily get the moment generating function, and it turns out to be 1 minus twice t to the power minus n by 2. This is the same formula as that for the gamma distribution. You can verify yourself. Now here we have a couple of lemmas that we can prove quickly, that if x1, x2, xk are k independent chi-square random variable with degrees of freedom n1, n2 and nk, then their sum x1 plus x2, xk also follows chi-square distribution with degrees of freedom n1, n2, nk. So the hints is really, you have to recall that the moment generating function of the sum of these random variables is equal to the product of the individual moment generating functions, provided they are independent. So this is where the independence comes handy. And so if you take the products with each, so xi has following chi-square with ni, so n will be replaced by ni. So the product will be 1 minus twice t to the power minus of, it will be summation of ni. So that's why hence this result. So sum of chi-squares is chi-square. The degrees of freedoms just get added. Now here is the relation with normal distribution. If x follows n 0 1, then x square follows chi-square with 1 degree of freedom. Now this is something as is an interesting exercise. So if x is a real valued random variable, x square will be a non-negative valued random variable, and if x is continuous, x square will also be continuous. Why? Because recall the definition of a continuous random variable. So if I ask you what is the probability y equal to any number small y, then this will be equal to probability x taking two values. X can be either plus or minus. So this could be either y, square root of y, insert, so it's a insert plus minus square root of y. So this is what it would be. Y is positive, obviously y cannot be negative because capital Y is a non-negative valued random variable, so it can take only non-negative values with positive value, but this will be equal to 0, right? Why? Because x is a continuous random variable, so this will be, so this is a justification of why I have written this to be non-negative continuous. And now so this is the justification of why I am saying y is continuous, and why it is non-negative is trivial. Now in the same way we try to find the probability distribution of y, that is we find out the distribution function of y. So therefore in this case we are using this inequality, that if y is less than y, then that would mean mod x is less than equal to root y. And so we are able to express the distribution function of y again in terms of the distribution function of x. So what is has been used in this step? The fact that if x probability that x is between a and b is actually the difference of fxb minus of fxa. This again follows from the definition of distribution function and additive property of probability. Now we use the same argument, since the distribution of fx is normal, so it's a continuous distribution, and therefore fx is differentiable. So differentiating fx, we get the density of fy. So we get the density of fy here, and it turns out to be 1 by root over y, the density of fx at y plus the density of fx at minus root y. And substituting this in the standard normal formula, and that is here, we get this formula. This 2 gets absorbed because you see y root y square and minus root y square are one and the same, so it will be just 2 times that of the standard normal density at y, and square root of y square is y, so you get this. And now if you recall what is square root of pi, square root of pi is gamma half. So now if you just compare here, so this will be equal, this is, you put n equal to half here, so this is what exactly the formula that you have gotten. So hence we conclude that x square follows chi square with 1 degree of freedom. Now the next lemma is that if x square, x1, x2, xn are IID n01 random variables, then summation of xi square would be chi square n degree of freedom. So this is really the I am leaving this as an exercise for you based on the lemma 2 and lemma 1. See, by lemma 2, x square, each xi square will be chi square 1 random variable, and they are independent. So their sum would be again chi square by lemma 2 and by lemma 1, and this sum will have degrees of freedom equal to the sum of their individual degree of freedom. So there are n random variables, each of them chi square 1 degree of freedom, so their sum will be chi square n degree of freedom. So that's it. So chi-square, this is a brief introduction to chi-square distribution. This is a mighty important distribution in probability and statistics. You will come across it if in many contexts. For example, in testing of hypothesis, there is a subject in statistics, testing of hypothesis, and also relate in the study of continuous distributions in probability and statistics. Thank you.